Hello everyone, my name is Lisa Choe. I'm a research structure engineer at the National Institute of Standards and Technology. This presentation will talk about behavior of composite floor assemblies subject to fire, mostly focusing on influence of slab reinforcement. So the current fire safety design in the United States is essentially based on fire ratings of isolated steel members and assemblies. And this method is not cheap. We spent about $60 billion on passive fire protection for commercial building construction, but it does not really provide any useful insight into help making the risk-informed design decisions, such as uncontrolled fire events. There has been lots of significant efforts in the United States to introduce more cost-effective and safer design methods, mostly based on the lessons learned from the Cardington test and other European research, but there are still lack of knowledge on fire resilience of full-scale structural systems commonly built in the United States. So currently, the NIST is taking a lead on these efforts by conducting a series of large-scale experiments using this two-story steel-framed building, as you can see here in this photograph. The goal of this research is to provide technical basis, including the fire limit states of composite floor systems commonly used in the US practice, and also very good useful data sets with a quantified uncertainty in the measurements to guide validation of a computational model that could be used for the fire safety design. So in this test program, we planned a total of 4 fire experiments on 6.1 meter by 9.1 meter composite floors as a part of these two-story steel gravity frames. The fire condition was created using the natural gas fueled burners rated up to heat release rate of 12 megawatt. For mechanical loading, we used 4 sets of the actuators mounted at the basement of the test compartment to apply the gravity load that conforms to ASC 7 load combination for extraordinary events. We conducted 2 tests so far, test number 1 and 2. The main difference between the 2 tests is essentially the reinforcement scheme used in the test floor slab. In test number 1, we used the cold rolled wire mesh with the steel area of 60 millimeters square per meter. This is exactly same as the minimum shrinkage reinforcement permitted in the United States construction practice. So we think this first specimen is control specimen to provide the baseline data for US practice. In test number 2, we used the number 3, the rebars at 30 centimeter spacing. This particular reinforcement scheme was designed using the New Zealand slab panel member methods developed by Professor Charles Clifton at the University of Auckland. This method is essentially incorporating the tensile membrane action with the advanced version of Bailey's methods. And this slide shows the test assembly and fire compartment used in our experiments. The floor assemblies essentially consist of lightweight concrete slab cast on this trapezoidal the metal decking supported by this wide flange shaped beams. The floor slab is basically acting compositely with the steel beams through headed studs at 30 centimeter spacing. The calculated composite action was about 65% of the tensile strength at ambient temperature. And then for the beam connections, we use this shear tap, the fin plate connections, which is commonly used in the United States. The moisture content of the concrete before fire testing was in the range of 6 to 8%. And applied load ratio of the composite beams within the test bay was in the range of 0.2 to 0.3. And this is the photograph showing the inside of the test compartment. As you can see, the steel frames actually protected with SFRM for 2-hour fire resistance rating, which is commonly used in the US practice. And then also the fire, and as you can see here, the columns actually not directly exposed to fire with the exception of beam to the column connection region. And fire was actually contained with this non-load bearing the partition walls. and we have a large ventilation opening on the exterior wall. So fire experiments were conducted such that we applied a mechanical loading at ambient temperature, then increased the heat release rate of the burners to create the compartment fire condition. In test number 1, the fire duration was 107 minutes. However, we have to remove the actuator loading at the same time. This is mainly because of the large structural integrity failure of the test floor slab, which I'm going to talk about later in this presentation. But in test number 2, the fire duration was 131 minutes. At the time, we basically observed the deformation of the exterior wall. So because of the safety concern, we had to remove the test fire. However, we didn't remove the mechanical loading for the 2-hour cooling phase. So this is the test video showing inside of the test compartment. As you can see, the natural gas burners created very uniform upper layer gas temperature in excess of 1000 degrees Celsius. The evolution of the gas temperature in test number 1 was very closely related to the standard furnace fire curve. In test number 2, the gas temperature also increased in a similar fashion, but was slightly higher than the test number 1. So now we are looking at the temperature of the composite beams at midspan. The values plotted here is basically the average temperature readings from the 3 9.1 meter composite beams within the test bay. The error bars basically indicating the standard deviation. As you can see, the temperatures of the protected bottom flange and the middle web actually increased to in excess of 800 degrees Celsius on average. And also the temperature increase in other parts within the composite cross sections between the two tests are pretty comparable. So we also installed the lots of thermocouples within the concrete slab, especially away from the steel frame underside. This figure is basically showing the temperature evolution in the mid panel region. The orange curves indicating the test number 1 regions, black curves indicating test number 2 regions. As you can see here, the temperature increase within the slab are very similar to each other between the two tests. So I'm going to play the video showing the top of the floor assembly, which is recorded during the test number 1. So as you can see, following the ignition of the burners, the heated floor slab is continually sagged throughout the fire exposure period, and eventually making the huge breach in the middle of the test floor, exposing the hot glowing deck underneath, which could be pose another risk for the ignition source beyond the compartment of origin. So this slide shows the vertical displacement measured at the center line of the test floor assembly. The orange curves indicating the test number 1 regions, black curves indicating test number 2 regions. As you can see here, given that the thermal response of the composite floor assembly was very similar between the two tests. However, the reinforcement scheme can make a huge difference in the vertical displacement behavior of this composite floor assembly. For example, for the test number 1 specimen, which is lightly reinforced with the wire mesh, actually start to making a center breach around the mid-panel vertical displacement of 30 centimeter. On the other hand, the second specimen reinforced with number 3 rebars actually deflected much more slowly, and this specimen actually maintained its structural integrity for longer duration of the test fire and at larger vertical displacement. So we can clearly see the difference between the two tests from these post-test photographs of the test floor slab. In test number 1, the large crack openings actually developed along the test bay column grid during the early phase of the fire loading, and these slab edge cracks actually allowed the rapid increase in the vertical displacement at the mid panel, eventually leading to the center breach following ruptures of the wires. In contrast, The test number 2 floor slab is actually exhibited very thin cracks distributed across the test bay. So you can clearly see that the number 3 rebars helped maintain slab continuity during the fire exposure, and also more effectively control the crack openings in the middle of the test floor. So summary and conclusions. In the first experiment, we tested the composite floor assembly that was designed and constructed following the common US construction practice, including the prescriptive design details for the 2-hour fire ratings and also the minimum shrinkage reinforcement in the composite floor slab. Even if the specimen and this particular assembly is actually rated for 2 hours, but the structural integrity failure can achieve at 70 minutes because of the early formation of the edge cracks and also the insufficient ductility detailing of the heated floor slab. And this study clearly indicates that the prescriptive design is not always a safe and conservative method. And the test number 2 essentially confirmed that the adequate design of the slab reinforcement is necessary to improve the fire resilience of composite floor, the system under fire exposure. We particularly use the tensile membrane action for detail to determine the slab reinforcement detailing, which essentially allow delaying the vertical deflection of the floor slab and also effectively control the crack openings. Now we are in the preparation of test number 3. This particular test is more focused on the measurements of the failure mechanisms of composite floor assembly in a membrane action. And the specimen will be the same with the exception of the secondary beam, which will remain unprotected during the fire exposure. With that, I will end my presentation. Thanks for your attention, and I will take any questions from the audience.